Governments deploy specialized systems to track journalists covering stories powerful institutions want hidden. Watch this data packet in transit, suddenly diverted and captured. This exact surveillance architecture operates at a commercial scale. The tools used to build behavioral profiles and location histories rely on these same underlying methods. Notice how the vector arrows piercing the nation-state target and the commercial target are identical. The technical process of interception remains the same. A targeted surveillance protocol and a commercial data harvesting net rely on the exact same structural vulnerabilities. This channel covers cybersecurity and digital privacy every Monday and Thursday. Subscribe and hit the bell so you do not miss a video. Analyzing the defenses used by high-value journalists allows us to reverse engineer their practices. This provides a systematic framework to neutralize commercial surveillance on your own devices. This architectural schematic displays 3 physical layers where digital communication is compromised: device, transit, and network. We start at the endpoint. Device compromise bypasses transit encryption by infecting the hardware itself, making transit encryption irrelevant. Pegasus is a documented example of this vector. It utilizes zero-click exploits, where a malicious payload executes upon the receipt of a message. This requires no interaction from the user. The device is compromised before the recipient even opens the app. This compromise grants access to the entire system. An adversary can monitor memory resident data, live microphone and camera feeds, access to stored passwords, and historical location logs. Journalists defend against this vector by performing regular device restarts to clear memory resident payloads. They also prioritize rapid operating system updates to patch the specific zero-click pathways that these exploits require to function. For a user facing commercial threats, maintaining current OS versions closes the known vulnerabilities that zero-click payloads exploit, preventing the code from executing in the first place. The second vector involves communication interception during data transit. End-to-end encryption changes this layer. When properly implemented, the carrier, app provider, and ISP see only encrypted ciphertext. Only sender and recipient possess the keys. When adversaries cannot read the message content, they focus on harvesting the metadata. This includes timestamps, sender and receiver identities, and the size of the data packets. Platform architecture determines exactly how much of this data is exposed. Mainstream apps like WhatsApp maintain a broad metadata architecture. Signal, however, is designed to retain only the date of account creation and the date of the last connection. To counter metadata surveillance, major news organizations route systems like SecureDrop through the Tor network. This masks the source and destination of the data, stripping away identifiable connection patterns. Moving daily communications to a low metadata protocol like Signal neutralizes transit interception and removes the data points that the commercial metadata market relies on. The final surveillance vector operates at the structural level: network surveillance and traffic patterning. Even with encrypted content, observers use the timing and location of packets to map your associations and physical movements. Internet service providers log cell tower connections and IP routing data. They package this behavioral information and sell it to commercial data brokers. Journalists use virtual private networks to tunnel and mask their IP routing from local observers. For sessions requiring higher anonymity, they use Tor to route traffic through multiple layers of encryption. A reputable VPN hides your IP address and traffic destinations from the local ISP, cutting off the raw data supply to commercial brokers. Applying every high-level defense simultaneously often leads to operational fatigue. Security that is too difficult to maintain during daily use eventually fails. Operational security, or OPSEC, is a 5-step cycle engineering privacy proportional to the threat. Step 1 identifies critical assets. Step 2 maps adversary capabilities. A data broker has different tools than a state agency. Step 3 maps vulnerabilities across the device, transit, and network layers. Step 4 assesses exploitation probability. Step 5 applies countermeasures strictly proportional to risk, minimizing unnecessary difficulty in your daily workflow. Applying this framework reveals that most users do not need burner phones. They need a specific set of tools configured to address their specific threat model. Mapping tools onto our 3-layer model creates a pragmatic defense. Signal and Proton Mail secure the transit layer, protecting content and metadata. A VPN secures the network layer against ISP logging. Regular OS updates and hardware keys secure the device layer, closing exploit pathways. Tools like Tails OS are effective for high-risk journalist tier threats, but their operational friction exceeds the needs of most users. Effective digital privacy results from applying specific cryptographic tools to their corresponding systemic vulnerabilities. The practical equation involves device integrity through updates, transit cryptography with Signal, and network obfuscation via VPN. The OPSEC framework functions as a continuous, ongoing cycle of identifying risks and adapting your countermeasures to meet them. Evaluate your own setup. Which surveillance vector presents the biggest vulnerability for you today? And what is your plan to address it? Let me know in the comments. Subscribe and hit the notification bell for new cybersecurity breakdowns every Monday and Thursday. Next, I will walk through the exact tech stack I run on my own devices. Commercial data brokers rely on the same interception mechanics as nation-states. Adopting these journalist-grade defensive frameworks provides a tested methodology for securing individual privacy. See you Thursday.